you for the introduction. My name is Shintaro Sato. I'm very happy to be here, finally, to give a talk on the quantum computing at Fujitsu. This is the outline of my talk. I explain the background first, then I explain the quantum computing activity at Fujitsu. And then I also talk about the quantum-inspired technology, digital annealer. Fujitsu has been working on the computing technology for years. And we developed the supercomputer K, Fugaku with RIKEN. They were the world's fastest supercomputer at that time. And now we work on the quantum-inspired technology, digital annealer, and also we work on the quantum computing. Okay. We recently made a press release on the new computing platform, computing as a service. This platform is easy to use and help the customer to solve their problem. Actually, customer can use various computing resources, including HPC and digital annealer, and in the future, quantum computer. This slide explains the classification of the quantum computers. Maybe you all know that. And we work on basically quantum gate-based system in the left panel. And as for the Ising machine-based model, we actually implement it onto the CMOS circuit. That is our digital annealer. First, let me explain quantum computing at Fujitsu. This slide explains Fujitsu's strategy for quantum computing. Basically, we try to cover all the technology layers from device level to applications with the world-leading research institutions. Because we don't know the final solution for the hardware yet, we try to put emphasis on the software technology. As for hardware, we work on the several types of hardware with the world-leading institutions like RIKEN and TU Delft. And we also try to develop applications with end users from this year using our newly developed quantum simulator. Here, let me briefly explain the hardware technology. First, we work on the superconducting qubit technology with Professor Nakamura of RIKEN, who demonstrated the superconducting qubit for the first time in the world about 20-some years ago. Actually, we launched RIKEN RQC Fujitsu Collaboration Center last year. There, we try to develop the hardware and software technology to realize a quantum computer as many as 1,000 qubits. And then we also try to develop application using such a prototype quantum computer. As for we also work on the diamond skin qubit technology with TU Delft. Later, I will explain this in details. Okay. And as for the software technology, we basically put emphasis on the error suppression mitigation or correction technologies. As for the error suppression technology, we work with Professor Emerson, now with Keysight Technologies. And as for the error correction technology, we work with Professor Fuji of Osaka University. Actually, we established the Fujitsu Quantum Computing Joint Research Division at Osaka University last year. There, we basically work on the R&D of quantum software for forward-trend quantum computing, including error correction and logical gate operations. Here, let me explain a little bit about our chip structure of the superconducting qubit chip. As you can see, it's a kind of cross-sectional image. As you can see, our interconnect is from the back. So it's a kind of 3D contact structure. With this chip design, we can make it larger, just tiling the 64-qubit chips, for example. So you can see this chip at our booth, so please come to our booth. And so, as I said, we work on diamond spin qubit technology with TU Delft. Basically, we try to make a modular-type quantum computer using these technologies. And actually, that quantum module is consisting of the electron spin and the nuclear spins around it. And we try to actually, the quantum module are connected by photonic links, so that we can make it larger scale very easily. So this approach can allow for the high temperature operation and good scalability, we believe. And we also we work on this technology from the like material level. We now investigating the team vacancy as a color center for our computing system, and also the work on the on-chip 3D integration of the optical and electrical circuit. Recently, I mean, this year, the TU Delft actually formed logical qubit, which consisting of the 5 spin qubit of carbon-13 and electron spin and nitrogen nucleus spin. And actually, TU Delft demonstrated the fault-tolerant operation of the encoding and the logical gate and the stabilizer measurement. So details are described in this Nature paper. And this year, actually, last March, we developed the world's fastest 36-qubit quantum simulator by using our supercomputing technology for Fugaku. Actually, to do this type of simulation, we really have to do like parallel computing. And communication between computer can be an overhead. So basically, we developed the data relocation technology so that we can reduce such overhead as much as possible. From then we can now, our simulator was twice faster than the simulator developed by other institutions. And now, actually, last September, we have actually developed an even larger simulator with a 39 qubit. And now, using such simulator, we try to develop application with end users, including Fujifilm and Tokyo Electron, in the field of the quantum chemistry and manufacturing and the finance. And we also try to prepare a library for our platform. So we work with a startup like Qnasys to implement such library on our platform. Then next year, we are planning to develop application with end users using our real actual quantum computer developed at RIKEN. And then very recently, we made a press release on the software technology called Computing Workload Broker. Actually, with this technology, what we try to do is try to optimize the use of the computing resource based on the customer needs. Customer needs means accuracy or cost of time. So actually, we actually recently demonstrated this technology using the quantum chemistry calculation as an example. We developed 3 technologies for this. One is the technology to judge the accuracy of the given quantum algorithm, not quantum, quantum chemistry algorithm. And then another is the technique to estimate time for the computation using each algorithm. And also, the last technique is the technology to optimize the use of computing resource based on such information and customer needs. So now we try to develop a new software technology using our newly developed quantum simulator. This is about the roadmap for our gate-based quantum computing. We have just developed the 39 qubit quantum simulator. And then next year, we're gonna release a superconducting quantum computer with a 64 qubit at the RIKEN RQC Fujitsu Collaboration Center. And 2 years later, probably we're gonna release an even larger number of qubit system, probably a few hundred qubit. And we are planning to implement error correction technology on that computer. And maybe 2 years from that, then we are planning to release a superconducting quantum computer with more than 1,000 qubit. That's our rough roadmap. Okay, next, let me explain the quantum-inspired technology, digital annealer. Actually, as it takes some time to apply quantum computing to the practical problem, we actually developed the digital annealer as a quantum-inspired system. Actually, the digital annealer has been used by many users since its launch in 2018. Actually, we have several proprietary technologies like a parallel search or like a technique to handle the constraint encountered in the real-world problem. Actually, due to this good technology, now many users are using a digital annealer in the field of the manufacturing and finance and delivery planning. I'll explain the use case later. And then this is the roadmap for the digital annealer. We put in the market in the year of 2018 as a system to handle the 1,000-bit problem. Then later we developed a larger chip with about 8,000 bit. Then actually about 2 years ago, we developed the hybrid system consisting of the hardware and software so that we can handle the 100,000-bit problem with this hardware. So then this year, we then developed the fourth generation digital annealer. Let me elaborate on this. And actually, the fourth generation digital annealer has basically similar interface with the third generation digital annealer, but it has a larger computing core. So this fourth generation can handle the 100,000-bit problem without partitioning the problem. And also now, very recently, we actually even upgraded the system so that we can handle the 1 million bit problem. Okay? And because we don't have to partition the problem, our fourth generation digital annealer can solve the typical problem for 10 times faster than our older version. Okay? And then we also work on the middleware technology of digital annealer. Actually, to solve the problem using digital annealer, we have to adjust a lot of hyperparameter, and which can take a lot of time, depending on the problem. So basically, we developed the AI technology so that we can adjust such hyperparameter automatically. Okay? So now we can adjust such parameter very fast, and we can even get a better result. The details will be explained at this conference next year. Okay. And then this is a kind of benchmark of the annealing technology. Compared to the quantum annealing, CMOS-based annealing can handle a larger number of bits, up to 1 million bits, and they are all fully connected. Then, compared to the other CMOS technology, we believe our strong point is the technology to handle the constraints encountered in the real world. Okay? For example, TSP, a salesman can visit only one place at one time, not twice. That's a constraint. So we have a lot of technologies to handle such a constraint very efficiently. And from here, let me explain the use cases. First, the optimization of the big loading plan with Nippon Yusen, a big company in Japan. Actually, on-can carrier, each can must be loaded at a time at the predetermined intervals according to a predetermined loading plan. So to make such loading plan is a really difficult task. It's a really difficult problem. So actually, combination can be a lot. So basically, we optimize this loading plan using digital annealer, and we are able to reduce work hours by as much as 4,000 hours per year using our digital annealer. Okay. So next one is the optimizing. We optimized automobile production sequence with Toyota systems. Actually, at the car plant, actually we have to optimize the production sequence of the automobiles because we have different types and different colors, and it's very important for the cost reduction in the automobile makers. So basically, we optimize this planning using our digital annealer. And then now it was applied to the Tsutsumi plant, one of the plant of Toyota, and it's successfully. And now we plan to expand our business to the other factories of Toyota in Japan and overseas. And third case is the application to the IT drug discovery. Actually, as you know, the experimental search for the new drug requires an enormous amount of trial and errors, right? And the designing and evaluating drug candidate on the computer can significantly reduce the time and cost for the drug development. So basically, we developed the technology, the combination of the digital annealer and HPC to narrow down the drug molecule candidate. Actually, what we did is we made some model so that DA can roughly narrow down the candidate molecules. After narrowing down, we then use the HPC to do a molecular dynamics simulation at the atomic level. With this, we are able to find a stable structure, which agree very well with the experimental result. So we hope that our technology can be used in the pharmaceutical industry for the drug discovery. Okay. The last use case is related to the quantum error correction. Okay. We did this using digital annealer. Actually, it's a simulation, but anyway, we try to use the source code for our superconducting quantum computer for the error correction. So in the surface code, you have to do a single measurement. You have a single measurement result. And then using this result, you have to identify where the errors are, right? So to do that, you usually can use the like a minimum weight perfect match method, okay? But what we found is it can take time if the number of qubits increases, okay? So what we did is we converted the problem to an Ising model energy minimization problem so that we can handle this problem using digital annealer, okay? And this is the result. And to make the long story short, left figure is a bit small. The vertical axis is like a number of iterations, so time. The horizontal axis is the number of qubits. So minimum weight perfect matching method, I don't have a pointer, but anyway. Number of qubits n. The computation time of the minimum weight perfect matching method scale with n to third power, okay? But in the case of digital annealer, that coefficient is from 1 to 2. So that means we can do such a calculation with the digital annealer for less time, okay? So we also simulated the logical error rate. And then we actually show that logical error rate can be reduced by the redundancy of the qubit. So, but in this case, we really use a simple error model. So now we try to use a more complete error model to show the better performance of the possible better performance of the digital annealer for the decoding. Okay, this is my final slide. And we work on the research and development of the quantum computing in order to solve a societal problem in the future. It will take some more time for the quantum computer to become capable of solving real-world problems. So we continue to develop technologies to realize practical quantum computer and work together with end users to develop its applications. The digital annealer quantum-inspired technology is already in practical use and has a lot of use cases. We continue to work on consumers' problem by using our digital annealer and HPC technologies. Thank you for your attention. Maybe I have 1 minute to take questions. Okay. Oh, 1 minute.
So you were comparing your digital annealer to the other systems, other digital annealers, as well as the D-Wave, a physical annealing system, right?
Yeah.
It seems that yours has more qubits and more connectedness.
Yes, yes.
What is the difference then between that and the D-Wave physical system then? Is there any
What's the difference?
Yeah, differences.
Difference in performance, you mean?
Performance, usability, yes.
we cannot directly compare our result with their result because we cannot use their result. So, but anyway, at least we can handle the larger problem, of course, because we have more bit with the partitioning. That can be our strength, and also we have a lot of technique to handle the constraint. Some are at hardware level, so that can be an advantage. So we'd like someone to compare our system, their system, to see to see the better comparison. Yeah.